Okay, good evening, ladies and gentlemen. I'd like to thank you for coming back to our private pilot free ground school. It's totally free. So if you're an aviation enthusiast, you're looking to work on your federal aviation private pilot written examination, or it's really computer test examination, this is the place you need to be. It's free, won't cost you a thing. In our last segment, we talked about the 5 major components of aircraft. And I think we can go ahead and flip back from this page. Wrong way. There we go. 5 major components. They would be the fuselage, the wings, the empennage or tail section, the power plants, and they're not just engines, that's why we call them power plants, and the landing gear. Okay, and we talked about the various types of power plants, reciprocating engine aircraft, and jet engines, and we talked about the 4-stroke cycle process, how that works. So if you haven't seen it, you can go back to PP1 or the Private Pilot Module 1. This is Module 2. And you can just get the information that you need, because it's pretty vital information for ground school. And if you have any questions, concerns, you can email me at kienothomas@gmail.com. And today we are going to go into the second module. Okay, those are the many faces of Kieno, and that's fine. I'm Kieno Thomas. I'm an airline transport pilot and a multi-engine instructor. So, a little bit about my background. I've been around airplanes since I was like about 15 years old in the Civil Air Patrol and other, various junior OTC and all that. And then I just kind of moved on and kept moving up and moving up. So, I am very well aware of what you need. I've been taking these examinations, these computer test examinations for years. And so I am an expert and an authority on these tests. So moving right along, we're going to talk about induction systems. The purpose of an induction system is to bring outside air into the engine and mix it in the proper proportion and deliver it to the cylinders or the combustion chamber of the jet engine where the combustion occurs. We can control the amount of fuel and air so that it enters the engine. Now we control it by using 2 controls. We have a throttle here, and we have a mixture. The throttle in this case controls engine output, and the mixture, I can lean the mixture when I go into higher altitudes as the air gets less dense. So we're going to talk about that a little bit later. The throttle control, it controls the engine speed by regulating the amount of fuel and air mixture that flows into the cylinders. The mixture controls the fuel, like I just said. So, engine output, mixture. Now, in another setup, let's look at this setup. Notice we have a throttle and we have a mixture. And I want you to look at this. This is a fixed pitch propeller. The pitches don't move, or it's not adjustable. And so the throttle regulates a RPM gauge, or what we call a tachometer. All right. In this induction system, or in this setup, this is a constant speed propeller where we have a throttle, a propeller, and a mixture. And here you have a throttle, propeller control, and mixture. So it's just 2 different types of systems. And here I wanted to introduce the constant speed propeller. This propeller actually rotates inside this hub. It turns, and we can see this represents the propeller blade. So we can see the different angles that this blade can assume. We have takeoff, high altitude cruise, feather, flight idle, ground idle, and even reverse thrust, which is pretty neat. So as we talk about the induction system, we got to look at the carburetor. How do we get air into the system? So this is just a little journey that the air embarks on to get into the system and with the mixture. Now first, if you look here, we have a carburetor air filter. I got another picture to expose it so you kind of see what it looks like a little better, because this may not be as great a pic, but you can see the carburetor air filter. We got a nice angle on it. This is how the air flows into the carburetor and eventually gets to the engine. But there's a little screen there to keep dirt and all kinds of residue so it doesn't get into the engine, which is a smart thing. Now, this is a float type carburetor that's normally found in light aircraft. Alright, in this carburetor, you can see the air going in. So you could see, we saw our carburetor air filter. We can see how the air is moving into the carburetor, but before it gets here, it runs through a system of ducts and bends and stuff like that before it gets to this point. So the air moves through the duct before it gets here, and it comes up on this little area called a venturi, and we'll discuss that a little bit, but it's basically like a constriction. You see a wide open throat here, wide open throat here, but there's a constriction, and there's something very important that happens at this point. So at this point, with our air, we came in through the carburetor air filter. Now we're in the carburetor after going through the tunnel system. And we got to look at how fuel comes in, because we have fuel here, and we got to look at our float type chamber. This is where the fuel is metered into the system. Now you could see a ball here. It's just to maintain a certain level to make sure that fuel keeps coming in. It comes down through here, and up here to the venturi throat, and this fuel is actually vaporized. So that's something very important to remember at this point. And I jump here is the air mixed with vaporized fuel before being delivered to the combustion chamber. Alright, so here the velocity is increased and the pressure is decreased. So a couple things happening here. It's vaporized. As we get to this throat, the fuel air mixture moves a lot faster, and its pressure is decreased, and we also get a drop in temperature. Something very important we're going to need to pay attention to later. So this discharge nozzle is located in the area low pressure, and that's why we get the temperature drop. These carburetors are calibrated at sea level so that the highest fuel air mixture is delivered to the carburetor when the mixture is set to full rich. And that will be when this is all the way into the panel, not hanging out. You wouldn't see any shiny part of that knob. As altitude increases, density of air decreases. And if the fuel air mixture is not adjusted, then a richer fuel air mixture can cause engine roughness. So as we get up higher above 3,000 feet, typically we have to start pulling this out. Now, we don't just pull it out. If we actually rotate it in a certain way, which your flight instructor can demonstrate for you. I don't recommend a flight just playing with the mixture knob if you do not know what you're doing, because you can shut the engine down. Not a good look. So, like we said, if you go up with your mixture too rich, which means you're putting too much fuel and you're not reducing your fuel for the reduced amount of air at high altitudes, and this altimeter showing 9,900 feet, and you're going to have carbon buildup, an excessive carbon buildup on your spark plugs. All you have to do is lean your mixture, but not too much. Okay, so because the excessively rich mixture, well, they're saying it lowers the temperature, and we talked about the carbon deposits. Now, on the other hand, conversely, when we're descending and we're coming back down to our landing area, runway, landing strip, whatever you want to call it, then we have to enrich in the mixture, because now the air is getting denser. So we have the ability, when we go to higher altitudes, to minimize the vaporized fuel flow. We minimize it as the air density minimizes. So in a way, it's matching it. And then as we come back down and the air gets denser, then we enrich in the fuel air mixture. Now, this float type carburetor is a great system, but its icing tendency is a really big problem when pilots don't pay attention and do what they're supposed to do. But you guys don't worry about that, because you guys are going to have hot shot instructors, right? Now, at this venturi, we get a sharp temperature drop because of this constriction or squeeze point. One thing we have to understand is when we get around temperatures of 32 degrees Fahrenheit, that's normally freezing, but this is fuel, so it's not going to freeze, but you have to think about the air because air has water vapor in it or water content. So what we're worried about is condensation. A couple things going on here. This float chamber is actually vented, which means atmospheric pressure can equalize in here. This is why when the air comes in, it almost vacuums the fuel out for vaporization. So what we need to understand is as the velocity of something increases, its internal pressure decreases, and at this point the temperature actually gets colder. So if this temperature and pressure was kind of vented with the outside air and you were at very super low temperatures already, when it gets here it's going to get very low, and then we can get carburetor icing. And this is a bad carburetor. We do not want it icing. But you have to understand when you get into colder temperatures, and really not so cold because I'm about to show you a diagram in a minute. But when you start to ice up, and this is the throttle valve, what's going to happen is your RPMs are going to start dropping off and your engine's going to sound funny. You're going to hear like a, you know, and you'll be like, hey, that's not normal. This engine had a nice even hum this whole flight. Now we kind of got into cold air or high humidity with not so necessarily so cold air, and then you know you get the engine roughness. Now, to eliminate the effects of carburetor icing, airplanes built with float-type carburetors use carburetor heat. And on your panel right here, you can't see it, but the knobs would look like this: carburetor air, carburetor heat, pull hot, pull on. It'll just say, hey dummy, I'm the carburetor. So when it starts running rough, you suspect carburetor ice, you just pull a knob out, and your instructor will teach you the correct way to apply carburetor heat. Now basically what's going on here, we have heat just rerouted back to the carburetor through a system of the intake, you know, so the cylinders are just releasing exhaust air, but it's warmer, so we want warm air to be redirected back to the carburetor like I'm showing you here. So the warm air, the cold air was already coming in, but now here's the hot air control, and it actually lets the warmer air come in, and so that's how we melt the ice inside the carburetor. So what you will notice is that the fuel air mixture will be enriched, and you'll see the decrease in RPM. You'll add the heat. You may see a slight wobbling of the needle, and then it'll come back. But here's how carburetor icing has occurred, and then we introduce the carburetor heat switch into the system, and we turn that on, and then everything is business as usual. So it's really not. It's just something you need to be aware of. It's really not like a fatal thing, or like something like super crazy, like, oh, it's gonna kill us. No, you hit a little bit of icing, and you just detect it because you're going to be vigilant monitoring your instruments. Now, the cool thing about a lot of low-wing aircraft, they eliminate the threat of carburetor icing because they use fuel injection systems. The fuel injection system is basically composed of 4 components. We have a fuel pump. Here's the engine-driven fuel pump. We have an auxiliary fuel pump, or what people might call a fuel boost pump. This will be kind of used for starting, because if this is engine-driven, if the engine ain't running, guess what? It's not going to work. So we have an electrically operated auxiliary fuel pump or fuel boost pump. So just by the electrical energy in the battery, it'll just start moving some fuel in here to help out with the starting process. Then we have a fuel control unit. A fuel control unit, what would you think that would do? Well, actually, it's a fuel air control unit. So fuel and air. First you got fuel, then you got fuel and air mixed to these lines. And just like we showed you previously in our four-stroke cylinder system, fuel and air go in, and we have four horizontally opposed cylinders here with pistons in them, And what we're doing is we are fuel injecting, i.e. fuel injection system. So we're injecting fuel directly into the cylinders. There's no valves or popping and all that stuff, so it's a different system. The manifold is here. The manifold is the spider. It just sends the fuel control unit, pushes the fuel air mixture here, and then the manifold says, here, you feed. So it's like mama. It's like feeding her 4 kids. Here, baby. Here, 4 babies. Our cylinders. And mama's feeding them all. I know. That was a corny analogy, but hey. And then fuel discharge nozzles, which are the discharge nozzles that go right into the cylinder to spray the fuel air mixture in there. And we get a lot of things. So basically, in short, fuel tank moves the fuel to the fuel control unit. And it meters fuel based on mixture control settings. Here's a mixture lever. Here's a throttle and stuff. And it sends fuel to the manifold by a rate set by the throttle. Alright, so the throttle and the mixture both play a part in getting fuel into the engine. The mixture kind of changes the quality or the density of that fuel air mixture. As you increase in altitude, you want a lower fuel air mixture, or reduce the rate of fuel going in there for air. Diminishment, I don't even know if that's a word, but we'll work with that for right now. We talked about the discharge nozzles. The discharge nozzles are located in each cylinder head. They introduce air into the fuel and inject mixture into each intake port, where it is drawn into the cylinders for combustion when the intake valves open. So there are still valves there. Okay. Now, most single-engine aircraft have a service ceiling about 10,000 feet. This is because what happens is we actually lose power and performance as we increase altitude. Why? Because of lower air density. We're not getting as much bang for our buck. Even though we're getting the same volume entering the engine, that remains the same, but the density is lower, so we don't get as much pull from the propeller or kick in the piston to turn the propeller. So it's kind of like as we keep trying to climb, we lose power until we come back down to a lower altitude where the air is denser. Now, we can get sea level performance by using supercharging and turbocharging systems. Here's a turbocharger. This is probably like the more efficient system because it's not engine driven. The engine does not have to be running, and let's say we got our normal combustion going on. Here's our cylinders, cool air coming in, warm air coming out. Well, we have a wastegate here, and we have a return. Now, what we could do is we can close off this wastegate, right? And then this air goes, boom, it kicks back up here and then out. But what this is doing is it's turning a turbine connection, and what this is doing is actually sucking more air and packing it tighter. Kind of like a pressurization system, so that's pretty cool. But this is not dependent on engine output or anything like that, so to speak. It's the exhaust gases here, after closing this wastegate, kick back, and this turbocharger is connected to the turbine, which sucks in more air and really packs it into the cylinders at a more rapid rate. So even though we got lower density air, well, now we're pulling in a whole lot of volume, a whole lot more volume, whole lot more density. The supercharger diagram is different because normally this compressor is connected to some type of belt or chain. So it's kind of almost exactly like the turbocharger, but notice that these exhaust gases, they just go out. They're like, bye-bye. Once they're gone, they're gone. There's no wastegate kicking it around, connecting it to a turbine to suck air in harder. So this shaft will be connected to some type of chain or belt. Alright. So it's important to understand that this supercharger requires engine power to run on. Ignition systems. How do we get this plane started? Well, we get it started with a key, just like your car, but there's certain things going on here. Unlike your car, we have an on, a right, left, a both, and a start position. Now, when we start, and we let the key go back to the both position. But before we can even do that, we have to turn what we call a master switch on, which introduces an alternator and a battery into the system. But let's just slow down. So this is how we start. This is our ignition system. It provides the spark that ignites the fuel-air mixtures in the cylinder. So what we have here are magnetos, and we'll explain what these are, but we have lower wires, which are light blue, going on cylinder 1, 2, 3, and 4. So there's blue wires, a lower magneto, and an upper magneto. We have upper and lower spark plugs, which just make performance great, fuel-air mixture burn great. It's good, and in case one fails for redundancy, we have another one. So that's one of the things. You'll hear that word redundancy a lot in training. This is redundancy. You say, now, I don't know what that word means. When something is redundant, it means it's a backup. It's done for redundancy. The backup, if one fails, then we got a backup. Okay. Magnetos, upper lower wires, the spark plugs. Here's the cylinders. Okay. All right. Okay. So these magnetos are self-contained. They're engine-driven units that supply electrical current to the spark plugs. All right. It uses a permanent magnet to generate electrical current, completely independent of the aircraft's electrical systems. And that's like it's a weird way, but we'll stay with that for right now because I don't want you to get too lost. Now this diagram shows a dual ignition system. Like I said, there's two sets of wires coming from the magnetos going to each cylinder, and there's two spark plugs. And like I said, it's for improved engine performance. You can control the operation of the magnetos here with the on-off switch. But this is the ignition switch. It's on, right magneto, which is right here, left magneto, which is right here. Both, where you can have them both operating, sending electrical energy to the spark plugs, and in the start position. So that's typically the positions that we have. Normally keep them in both when we're doing our normal operations, but before takeoff, there's certain tests where we have to test the left and the right magneto during what we call a pre-takeoff check or a run-up. We do something called an individual mag check and then the differential. So as we turn this key to the right, left, then both, and then right, then both, there really shouldn't be too big of a difference. There's tolerances, and you have to consult your pilot operating handbook in order to know what the tolerances are. And the differential between the right and the left. When we got to know what it is at when it's at both, where it is when it's in the left position, where the needle is when it's in the right position, and then we have to note those, but your flight instructor will show you that. Now we're going to talk about abnormal combustion. Remember from before we had our 4-stroke engine cycle: intake, compression, power, exhaust. Well, when abnormal combustion occurs, this does not happen. During normal combustion, the fuel-air mixture burns in a very controlled and predictable way. The process happens in a fraction of a second. The mixture burns to the point where the spark plugs are ignited, and the normal combustion causes smooth buildup in temperature and pressure that makes the expanding gases deliver most of the force to the piston, kicking it back down at the precise time of that power stroke. So this is timed like within a fraction of a second. So it's got to be dead on. Now detonation occurs when an uncontrolled explosive ignition of the fuel air mixture inside the combustion chamber. Okay, so we don't like detonation because it's uncontrolled. We want everything in this system, this 4-stroke engine cycle, to be controlled. We don't want stuff just doing what it wants to do. Alright, because what happens is we can get excessive temperatures that could lead to engine failure, piston, cylinder failure, crack valve, all kinds of like madness could happen. And so this is why we don't like detonation. Whenever the plane is detonating, the best best case scenario is overheating or engine roughness. Worst case scenario is, some part fails in the engine and you got like complete power loss. So what do we do to prevent detonation? We have to use the recommended aviation fuel. Typically, most general aviation aircraft use this 100 LL, which means low lead. 100 low lead. There's 8087 red. There's 130 green. 100 low lead is blue, and jet fuel is typically clear. All right. So we can always go up a grade, but we can't go down a grade when we use, because these fuels are designed to take certain temperatures and pressures. And that's the whole part of the burn and even process. This doesn't have the oomph or the wherewithal to stay with the pressures and temperatures this can. This doesn't have the same thing. So we go up the aviation fuel grade, not down. Detonation has been described as a metallic rattling coming from the engine compartment. So these guys, they may hear like a tapping or something like that. And that is not something you want to hear before takeoff. You might want to shut the plane down. Detonation again. If you suspect that your engine is detonating, you can help keep the engine cooler by retarding the throttle and climbing at a slower rate. But you're going to see some temperature indications, probably going up into the red. So with the vertical speed indicator, which we'll discuss later, you want to maybe fly level. You might want to reduce your power a little bit, and you might want to get that nose from out of there to down here, which a climbing attitude would be where the nose point up this way. But this airplane is a pretty level flight attitude and is allowing more airflow to come into the engine to keep that temperature cool. Detonation can also lead to another problem called pre-ignition. Pre-ignition occurs when the fuel air mixture is ignited in advance of the normal timed ignition. We want ignition here in the power stroke, but if it's like igniting before, dude, it's not gonna be good. Now this is caused by residual hot spots in the cylinder, such as small carbon deposits on a spark plug. So our spark plugs here. Now notice we have two because we have a dual ignition system. So we could have twice as much of a chance of running into pre-ignition if we don't go through the proper checklist. We don't do what's recommended by the pilot operating handbook. So we want to make sure we do things by regulation and we do things according to the pilot's operating handbook. Again, it could be a residual hot spot. It could be cracks in the spark plug insulation. Or it could even be damage, to like the cylinder here. So you just want to be careful when we deal with these things. Now, pre-ignition and detonation can occur simultaneously. So you don't know what's happening. You're still going to get the engine roughness and high temperatures. So it's kind of difficult to distinguish between the two. But high temperatures and engine roughness is not anything you want to be flying. And you would land as soon as practical. All right. It's not necessarily an emergency situation, but you really need to get it tended to. And I'd say the lower flight time that you have, the more it is an emergency. But in both cases, you want to try to lower the cylinder temperature. Like I said, reduce the throttle. You can also enrich in the fuel air mixture and lower the nose attitude. Now we get into fuel systems. Typically, there's two types. Those that require a pump and those that are gravity fed. Here we have one fuel system that requires a pump. Here we have one that's gravity fed. We'll talk about the gravity fed one. We're going to see a lot of charts and diagrams during your training, and it's just this is just to let you kind of have a visual representation of what's going on. Now the fuel system is all in here. Doesn't even look like this at all. But it's trying to tell you that, listen, your fuel tanks are above the engine. This is what we would call a schematic diagram. And it's showing you how a system moves or operates. Okay, so we have a fuel tank here with a vent, a fuel tank here, a vented filler cap. So both of the tanks are vented for equalization. And these tanks flow down into a fuel selector valve and then a fuel strainer drain. And then there's two paths to the engine. There's engine primer. This is a manual pump that we use to inject fuel into the intake ports. And then through the carburetor, and we already talked about our carburetoricing. So there's two ways to the engine. And then associated with this carburetor is a throttle and mixture control knob. Now this dark region is a fuel supply. And then this lighted area is a vent. Like we told you, that flow-tight carburetor has a vent. There's also a vent here and a vent here. So nothing gets vapor locked. We let the system breathe. Okay, let me make sure I covered everything. So here's our fuel selector valve we looked at. There's 4 positions. We could suck off of both tanks. We could suck off just the right, or we could suck off the left, or we could shut it completely off, completely closing off fuel to the engine. I talked about the primer before. Here's an engine primer. Here's a primer here. It's a manually operated pump that pumps fuel into the engine intake ports to assist with the starting of the engine, because cold weather, some engines is really hard to start in cold weather. Airplane engines as well, not just your car engine. Now the other type system is a fuel pump system, usually found in low-wing aircraft because the fuel tanks are below the engine. So the engine needs a little help getting that fuel to itself. So the fuel boost pump, which is electrically operated, like we said. An engine-driven pump is not going to work unless the propeller's running. So this fuel boost pump provides fuel under pressure. And in case this engine-driven fuel pump does not work, this fuel boost pump or auxiliary fuel pump can back it up. With fuel pump system, it'll normally include a fuel pressure gauge, which can help you detect fuel pump malfunctions. You know, if it drops below a certain level, then you turn the fuel boost pump on to keep steady fuel flow to the engine, because of any trouble or interruption is could cause a vapor lock. It could cause a vapor lock, and with some airplanes, it makes it virtually impossible to restart the engine. See here. Of course, with the fuel system, we have fuel gauges: a left tank, right tank. Sometimes you'll just have one fuel gauge representing your total fuel. But these fuel gauges are normally grouped with the engine monitoring gauges. Fuel selector valve, we told you what that does. Fuel system components. This is a fuel strainer drain. Now, this is the lowest part of the fuel tank. And at this point, any sediment or water, garbage, trash that should be in the fuel system is going to come right down here. This is actually a pin that pierces into it, and then it allows fuel to come down. And it gives this pilot a visual representation of what's going inside that fuel tank. The heavy contaminants are going to settle to the bottom, so when he pierces at the bottom, it's going to come back. And it's like spring-loaded, so don't worry about, oh, you know, fuel's going to be dripping out. That's not the case. This refueling slide just helps us. It's a part of the fuel system lecture, and basically, when we refuel, you know, there's normally the fuel's replenished through a fuel cap, and you can see the guy with a nozzle, just pumping the fuel like you would your car, or very similarly. But we have to keep in mind that a ground wire should be attached to the aircraft in the truck or refueling equipment, because the major hazard is possible combustion of fuel by sparks that cause the fumes to ignite because of the static electricity that it discharges between the refueling equipment and the aircraft. Oil systems. Oil systems. In order to have a happy engine, we got a lot of metallic parts here rubbing together and a lot of heat being caused. And so just like your car, needs oil for lubrication. There's also normally a dipstick area somewhere around the engine cowling so you can check your oil level, because you want to check your oil quantity before each flight. You need oil. Do not play with it. This is not a game. You can't. It's not like your car. You can pull over and check the oil. So you want to consult your aircraft's pilot operating handbook for minimum operating quantities, and do not fly without the minimum operating quantity. Now, there's two types of systems, oil systems. We have a wet sump or a dry sump system. Okay, and it's pretty simple. In the wet sump system, all the oil is carried in the sump, which is in the engine sump, which is a integral part of. It's just a part of the body of the system. And a dry sump actually has a separate tank. And here's our separate oil tank. The engine's all the way up here, but there's a separate air tank. And then there's lines that you got oil suction line here that brings it back, and the oil returns and goes through a separator, and then starts a journey all over again. So that's really the major thing we need to be cognizant. What type of sump is your aircraft, the particular aircraft that you're flying, because all that information is in the POH. It will tell you. For our oil system, our oil pressure indicator gives us a direct indication of what's going on with the oil system. Here, anytime a needle's in the green, that is good. We like green. We don't want it in the red. We don't want it in yellow. There's no yellow here, but there's red. And this needle's in the green, which tells me, and this is oil temperature and pressure, that tells me my system is working fine. And you would glance at it. If you got a below oil pressure, that means that the oil's maybe not pumping through the system. And if that's a problem, because that means that the oil's not circulating through the engine properly to keep everything nice and cool like it should be. When it's above pressure, you could have a clogged line somewhere. So you didn't want your pressure in that red, and you don't want it below. You want it right in the green. And that's why they make that the green area. Now, if you detect abnormal oil pressure indication, it might mean vital parts are not getting the necessary lubrication. That's not good. Now, the oil temperature gauge is normally located near the oil pressure gauge, and we got our green arc, we got our red arc. We don't want to be in the red. We don't want to be too low. Now, after engine start, you might notice that the oil temperature may be low for a little bit. After engine start, it takes a little bit for it to come up. But you don't want to be 15, half hour, 45 minutes into a flight and not see that engine temperature come up. So keep that a part of your instrument scan. Your instructors will tell you how to do it. All right, I already talked about this. Cooling systems. There's also cooling systems in addition to the oil system. So we got a lot of things. Because even though we depend on oil to keep the internal parts cool, we even want air flowing around this thing. I'm telling you, we want to keep a nice, normal, happy engine, happy temperatures, not too high. And we don't want that engine, because all this stuff going on, there's a lot of heat taking place, or heat generation. Like I said here, the combustion process that takes place inside the engine cylinders produces major amounts of heat. And we don't want everyone high engine temps, because it can cause power loss, high oil consumption, and even engine damage. So even though our oil system is essential for cooling, we need additional cooling, like I just said. Most of the heat is dissipated or lost through the outside air flowing around the engine. So here are two examples. We can see the cowling opening. We can see the cowling openings here. And air is allowed to flow in here, man, and get in here and then escape, taking a lot of that heat with it. Now, this is less effective during takeoffs, go-arounds, or anytime we're at low speed and high power settings. And some of these aircraft have a fixed cowl opening like this. There's an opening, escape for air to get out, where you don't see one really here. So what we have built into these planes sometimes are cowl flap openings. And we have controls here. You can have a left, right, a front, rear, whatever. But you'll have some type of system or control in the cockpit. And here's another picture where it just, boom, it opens up air. It's kind of like, you know, if you had your window cracked, small opening up front, and then your back window, you just open up, and man, all that air just rushing in like, hey, let me in. Because there's a pressure difference. Some cowl flaps are kind of just built there just to, hey, we know these engines are going to get hot. There's a lot of cylinders here in this radial engine. A lot of pistons at work, so that air just coming through helps maintain the system. Some aircraft with cowl flaps could have a cylinder head temperature gauge that give you a direct reading on what's going on with one of your cylinder heads or one of your cylinders. So, like I said, red's bad, green's good, and that's typically what you will find in a lot of the instrument indications. Green is good, red is bad. You never want to be in the red, and yellow is caution. So it's kind of like your stoplight system. Green, you can go. Yellow, use caution because the light's about to change. Red, stop. You know, so there's a method to the madness. And then the exhaust system. It's a part of cabin heat and windshield defrosting. Now, this will be a little bit lower. This is a picture I found. This is the best picture I could find. But the muffler's in here. But we have a shroud, right? And what happens is this air comes from the outside, but it's warmed up here. But it's not mixed with the exhaust gases, i.e. the dotted line is saying, hey, look, I'm just hanging out in the middle, just getting some heat. And then I'm just going to go in here and keep the pilot and crew and passengers warm. And I'm going to keep this windshield defrosted. That's all. So the exhaust gases still go out like they're supposed to, but we just put a connection near the pipes or a muffler, and it just warms the system. So cold air, really cold air comes in, but you know how hot these cylinders get. So it's pretty cool how we utilize those the temperatures from those exhaust gases to help us out. Let's see here. I'm trying to see where I am right now. So, yeah. Now the exhaust system, if there was a crack in this system some way, or crack in these lines where exhaust gases could get in here and stuff like that, then that would be bad, because then we would stand a chance of getting carbon monoxide. And so sometimes in aircraft you'll see like a dead stop carbon monoxide detector. You mark down the date it's open, and if you see dark spots, that means that carbon monoxide is getting into the cabin. So it's just something we want to watch out for. We're going to talk about propellers. There's two different types. There's fixed pitch, as we talked about before in an earlier briefing, and we have a constant speed, and we'll go deeper into that. But right now, the constant speed propeller is a controllable pitch propeller, which means we can change the blade angle automatically when varied by a flight governor. The propeller here, the propeller pitch control, controls the pitch, and the throttle controls the power output. The electrical system, we're going to go deeper into this, but basically, this was a really big slide, and I couldn't get it all in. But the electrical system, most of these systems are equipped with and we'll show you a battery, a 14 to 28 volt battery. Okay, we have an alternator up here, we have the master switch here, an ammeter or load meter here, we have an avionics bus, fuses which protect the components, you know, so every component, radio, dome light, nav, we're safe because we have circuit breakers that will pop out. They'll pop out in the event that, you know, the system is overloaded. I showed you your master switch. Here's the alternator. The master switch is definitely needed during the starting sequence. Alright. The alternator, the battery is used to start the engine. Here's a starter, and it's connected to the battery. But after engine start, the alternator provides the electrical energy that's needed in the system. We talked about the battery, and then we talked about the bus bar. The bus bar is the connection between the system components and the appliances, the radios, transmitter, encoding, altimeter, nav light. So everything is protected. And we're going to go more in depth here, but we're running at the 45-minute mark, and I'm trying to keep this dissolvable because there's a lot of information. So I'm going to cut it right there. Again, Kieno Thomas, second private pilot module. Thanks for watching. Just to cover what we talked about. We talked about induction systems, how it works, air being introduced into the system, carburetor, the carburetor system, carburetoricing, fuel system types, gravity fed, pump fed, what else? Fuel systems, ignition systems, refueling, oil systems, cooling systems, the types of propellers in electrical system. If you have any questions or comments, I'm Kieno Thomas, and you can email me at kienothomas@gmail.com. That's KIENOTHOMAS@gmail.com. I will see you guys next time for Private Pilot Module 3. Thank you.